Good afternoon, everybody. Thank you very much for coming to this presentation. Today I have the honor to introduce you to Dr. Kirk Borne. He is currently the Principal Data Scientist and Data Science Fellow, as well as an Executive Advisor at Boss Allen & Hamilton. Before Boss Allen & Hamilton, he was a Professor of Astrophysics and Computational Science at George Mason University for 12 years. He also spent nearly 20 years at NASA working multiple projects, including the NASA Hubble Space Telescope, the NASA Astronomy Data Center, and the NASA Space Science Data Operations Office. He has extensive experience in large science databases and information systems, including expertise in science data mining. However, I think one of the most interesting aspects of him is that he's considered as one of the top digital and data science influencers nowadays. That means that if you want to learn about machine learning, learn more about data science, you only have to follow him. I follow him on Twitter, and he's always posting a lot of interesting posts about resources, free resources, on how to learn data science and machine learning. So if you want to get some start, where to look, what material to look, you just have to follow him. He's always sharing a lot of information to educate people. So please welcome Dr. Kirk Borne.
Thank you. Thank you all for being here. I'll use my class voice. Can you hear me back there? It's heading positively. That's good. So thank you, Dr. Lopez, for the invitation to visit here. We first encountered each other in person at a DC conference in DC, but you followed me on Twitter for a while, and when he first introduced himself to me at that conference, he says, he follows me on Twitter. I said, oh, you're the guy. But if you look at my account, it's over 250,000 these days, so that means I'm sort of like 1/400th as popular as Taylor Swift. Well, I'm on my way. But anyway, I love sharing knowledge about this field. I love sharing the stories in this field, both fundamental basic knowledge of data science, machine learning, AI, those topics, but also the applications of those. So today I'm going to be talking not so much about sort of those mathematical things, even though there's a lot of mathematics in the field. I'm going to be talking about sort of the important things if you choose to go in this career path. Now, the career path doesn't mean you become a data scientist. It means that you're a person who is going to become relevant in the modern world. So who here wants to have a job such that you are relevant in that job? Oh, gee, wow, everyone. Okay, so everyone wants to be relevant in the modern world. Well, the modern world is digital. Everything is data. Everything is coming through some kind of a device, sensor, like your phone, producing digital signals. Those digital signals we call data. Those data are being captured by businesses who are making decisions about things, creating products, selling things, doing all kinds of stuff, and they're making money off of that. So the jobs we have in the future will be, everyone will have something to do with digital technology, digital information, data. Okay, so the relevance is not just that for people who become essentially career data scientists, but people who just have a real job in the real world in the years ahead, because the real world has all this stuff. And so whether it's computer science or hard science or humanities or marketing or social sciences of any kind or art or sports, it's everywhere. I mean, one of the main places you see this is in sports, and I'll tell you a bit about that in a second. But just as we get started here, I do want to say the slides are available that you see on the link here. The link will be appeared at the end as well. And so if you want to grab these things later or now or whatever, feel free to do that. So as was just described, my background is astrophysics. So I grew up wanting to be an astronomer. I always wanted to do that, and I did become an astronomer. I spent 20 years working at NASA on astrophysics data systems for NASA. And so in some sense you would say my night job was data, because as an astronomer, my night job was data, studying the universe. My day job was data. That is, what paid my salary was to do functional service work for the space missions, the astronomy space missions at NASA, specifically for the data systems. One of those jobs was with the Hubble Space Telescope. I was the project scientist, the NASA archive project scientist for the Hubble mission. Learned a lot about data systems and data, and from that perspective, not just at the data analysis, which I was doing on my own little research projects, but the data, huge repositories of data, which were being delivered to the scientific research community worldwide, accessing, using those data for discovery. So after I did that for several years, I moved on to another position, a management position, managing a project at the NASA facility for space science and earth science research, which is the Goddard Space Flight Center in Maryland, and I was managing a team of people at the Astronomy Data Center, which also included the Astrophysics Data Facility, which was the actual facility where we captured the data from multiple satellites, analyzed the data, made it publicly available to the world. So part of my job, besides managing this team of people, was to identify new data sets out there in the world from astronomy researchers who want to make those data sets available to the rest of the world. So once their project is done, what do you do with the data? Well, now, back then, basically you just had it on a magnetic tape in your drawer where it would decay, get old, go to pieces, turn to dust, and the data would be lost for eternity. Well, all these data satellites and missions that NASA launched, they're all paid for by you, your families, and when you become a taxpayer, by you. It's all taxpayer funded. And so Congress mandated that all data from these satellites would be preserved for all time in a digital library. It was paid for by public funds. So all these data we would capture and store there and deliver through an interface for all time. So back in 2000, before 2000, back in about 1997, I was about 10 years into this career I was just describing, and we were offered a data set at this data center that was 2 terabytes in size. Now that may not seem like much to you now, because you probably have 2 terabytes on those laptops you're looking at or not looking at. But back then 2 terabytes was an enormous amount of data. How enormous? Because I can tell you for sure, because 1 gigabyte, which is 1,000th of a terabyte, was so expensive in those days that I needed to write a proposal to NASA for $37,000 to get a 1 gigabyte hard drive for my computer. Now you have that on your thumb drives for free. Okay, so 1 terabyte was 1,000 times that, so it was ridiculously expensive, so therefore having that amount of data was crazy. And so this research team said, Kirk, we got this data set we'd like to turn over to the National Space Science Data Center, store it there for all time, good luck, have fun with it. Well, I thought that was really cool. I love working with data, doing discovery from data. So I went back to the facility managers and I said, hey, look at this opportunity we have to bring this big data set in, it's this 2 terabyte data set. And they looked at me like, what? And I go, like, what do you mean, what? And they said, well, you realize that here at the National Space Science Data Center, this digital library for space astronomy data from all of NASA's space missions, because there's always some experiment, not a bit necessarily a big one, but sometimes even a small one. There's always these experiments on everything that goes up in space. There's some kind of experimental package on there, dozens of them usually. So at the data center, we had 15,000 experiments of data. 15,000 experiments who had retired their data sets to our data center for all time to be stored there and served to the world. Those 15,000 data sets combined were less than 1 terabyte. So I was suggesting bringing in 1 more experiment on top of the 15,000. That 1 experiment would require them to triple the capacity of the data center. Add 2 more terabytes to the 1 they already had. Can you imagine that? Tripling the capacity of a national facility to bring in 1 data set on top of the 15,000 they already had. Talk about the straw that broke the camel's back. You ever heard that expression? I mean, that 1 little experiment, well, wasn't a little after. So I didn't know what to do with this. And my colleague said, well, if you could find some way to get NASA to fund this, we could go out and buy the resources and do this. So I really didn't know how to write a proposal for infrastructure because I was an astrophysicist. I studied colliding galaxies. That was a lot of fun. I didn't know how to write a proposal to buy infrastructure for a national facility. So a colleague of mine put 2 words together that I never heard before put together. He said data mining. So this was 1997, data mining. So data mining is the application of machine learning, which are mathematical algorithms that find patterns in data. So application of machine learning to data sets to find discoveries in data. I never heard that expression before, so I started digging into it and I found it really fascinating. So I was getting really into it because I love math as an astrophysicist, of course trained with math, I love math, and I said this is really cool, but I don't see the connection between all this cool math that I like with how I'm going to write a proposal to NASA to buy a piece of hardware. I mean, just because I'm geeking out over the math doesn't mean the people who hold the purse strings and who give money for this stuff is going to be quite as geeked out as I am about the mathematics here. So I said, I got to find some other hook. I got to find some other way to justify this, to make it seem important and imperative to people besides it's just more cool math stuff. Okay, so I was looking into this data mining and again the machine learning algorithms, which were the mathematical algorithms behind it, and trying to learn as much as I can, try to find that hook. And then one day in my office in 1998, which is this aha moment, which is identified up on the screen here, So in 1998, there was an invitation to a lunchtime talk. It came across my email. Well, this is not unusual because it was a facility with 20,000 researchers, data scientists and engineers. So there was like 2 or 3 or 4 talks every day of the year. All right, so it wasn't unusual to get an invitation to a talk, but this one was interesting to me because it said IBM researcher was going to talk about their data mining research project at the IBM Watson Research Lab in New York City. And I said, oh, cool, someone's going to be talking about this data mining stuff. I want to go hear what they have to say because maybe this will help me. Because again, I was learning the math behind it all. I was learning sort of the algorithms behind it all, but I was trying to find what is the real impactful thing that I can find in this field that will help NASA see the light, the value that it would bring to them. So I went to this talk, and I wish to this day I could remember the name of the speaker, but I swear she was like the most polished speaker, public speaker I'd ever seen. I mean, she had us eating out of her hands. I learned a lot of good skills in public speaking from her. So she knew exactly when to pause and have you think about it. So what she did in this lunchtime talk, she spent the first 30 minutes filling the blackboard behind her. We didn't have whiteboards in 1998. Filling the blackboard with equations. All those machine learning equations for data mining. And I'm sort of sitting there thinking, okay, that's cool, that's great, it's more math. If it's just more math, I'm still not getting the pitch that I need to make to those people out there. So I'm just wondering what's going on. And about halfway through this talk, it was lunchtime talk, so about half past the hour, she pauses and says, now I want to tell you about our summer intern program. Well, so that was like, what? I mean, from a very heavy mathematical lesson to talking about the summer intern program. And so she did one of those pauses where she just waited to see our expression on her face, and we all probably had puzzled looks because I know I had one. Like, where is she going with this? Yeah. And she said, yeah, we teach data mining and machine learning to inner city high school kids in New York City. Yeah, right. All that stuff on the blackboard behind us, filled with equations. You're teaching this to inner city kids in high school in New York City. Yeah, sure. And again, she had one of those pauses because she probably knew where our brain was going to be going, where she's like, I don't believe this. How is that possible? I mean, that was pretty dense stuff for people with PhDs in the room, okay? And she said, yeah, I teach this stuff in the context of the thing that matters most in their life. She pauses again. And I'm scratching my head. I said, okay, I am an Air Force brat. My father was Air Force. We lived in very small towns on purpose, because you don't put missile bases next to large cities. So I never lived in a large city. I don't know what the most important thing is in the life of someone who lives in the inner big city. So I'm just puzzled again. I'm puzzled again. And she said, yes, we teach this stuff in the context of the thing that matters the most to them, and that's street basketball. They live and breathe street basketball. Before school, during school, after school, they love basketball. And so what we do is we teach them about data mining in the context of basketball, because at that time, IBM had this machine learning data mining product called Scout, and then became Advanced Scout, which they sold to all the NBA basketball teams. Every defensive coordinator on NBA team owned this software. Every team in the NBA owns this software, where they actually stored the play-by-play histories from video, TV video. They captured every little play. How many players were on the court, what the court score differential was, how much time was on the clock, who had the ball, who passed the ball, who took the shot, what kind of shot, was it a layup, was it a pass, was it a jump shot, but whatever it was, all that information was encoded in a database, and then they could mine this database and predict what the next play would be at any given point in the game. And all the coaches bought this software to coach their teams because it was a miracle they could actually build a predictive model of what their opponent was going to do under any condition in the game. Amazing. They could actually predict the future of a game just from the previous history of the plays, of all the games prior to that. Well, when these interns, high school students, heard this thing, mathematic thing, science thing, data mining thing was relevant to what's important in their lives, this is basketball, they immediately decided to start learning math and science. I mean, she said that it was transformational in their lives. They immediately decided, I want to learn this stuff. Now, picture this. I'm imagining this. I don't know if she said exactly this, but I'm picturing this. That the peer pressure for these young people in inner city New York was probably not for academic success. The peer pressure was probably for other things. Family pressures, peer pressures, whatever pressures. It was probably not leaning toward academic success. All kinds of other stuff, particularly people who wanted a life as a basketball player, which a lot of these students probably envision themselves someday being. And so for them to all of a sudden pay attention to math and science and academics was very amazing. So if she had stopped right there, I would have been like, okay, I got what I need. This is really transformational in the lives of people to understand you can build these predictive models off this stuff, and if it applies to basketball, it's got to apply to a lot of other stuff. So I would have been satisfied at this moment if she had stopped right there, but she did not stop right there. She said one more thing. In 1998, 22 years ago, and to this day, after 22 years, I remember exactly what my thoughts were after she said it. Exactly. I don't remember exactly what she said. I got it more or less right, but I remember exactly what I thought after she said it. And what she said next was, she said, their metric of success for this summer internship program is the graduation rate of the students that go through their intern program. And she said, these students who go through their intern program come from high schools where the graduation rate is less than 50%. Less than 50% of the students in those schools graduate high school. They move on to other things, the family business, whatever. But the students who go through this intern program have a 97% graduation. And I said to myself, and I remember exactly the thoughts I had, I said, if this data mining stuff, which we now call data science, if this data science stuff has that much power to change people's lives, I have to do this for the rest of my life. So in 1998, after 30 years since being a young child, always wanted to be an astrophysicist, became an astrophysicist, worked at NASA, I changed course to working to building data literacy in all generations, not just young, not just middle-aged, but even reaching senior citizens who are feeling digitally irrelevant in the modern world. So this is my passion life. This is why I live on Twitter and I promote all that stuff, because I want everyone to know this is the world. If you have the power to work with data, read data, understand data, make uses of data, create value from data, you will have a guaranteed job for life and guaranteed job joy for life. Because you'll be doing stuff that's changing people's lives. You're doing stuff that can predict the future. And that's what I wanted to do, and that's what I started doing 22 years ago. Ultimately left NASA, then went to a university. As mentioned, I was a professor of astrophysics. They didn't know what data science was, so they hired me as a professor of astrophysics. I spent 12 years there, but I never taught an astrophysics course. I only taught data science. So we created the world's first undergraduate data science degree program. So we got state approval 14 years ago. We started operating the courses 13 years ago, and did that for several years until this company, Booz Allen Hamilton, came along and said, hey, well, why don't you just move this out of academia and just teach the whole world this stuff? And I said, okay. So there you go. So the world is data. Everywhere is data. You need to learn how to use data, work with data, understand data, and recognize data when you see it. So for example, this is just one example of a kind of data. This is sensor data coming off of airplane engines. And not just all airplanes, but it's just the Boeing aircraft fleet alone. Just look at the Boeing aircrafts which are in use in airlines across the United States. In 1 year, there's 20 terabytes per hour for every engine. Twin engine planes, typical 2.5-hour flights, typically 28,000 flights a day, 365 days a year. This one type of sensor is producing 1 zettabyte, that is 1 billion terabytes of data per year. That's one type of sensor. And there's this thing happening around us called the Internet of Things, where there's sensors being put on everything. And the estimation is in the next few years there'll be like 20 trillion sensors in the world. So we've already blown past the terabyte I told you about in that story, where we told you that data set had 2 terabytes, right? We've blown past that, past petabytes, and all of a sudden we're getting down here, just for one type of engine, a billion of those, which doesn't seem too far-fetched. We're going to get to 10 to the 30 bytes, which has a fancy word called the geobyte. I never thought we would get there, but I think we're approaching rapidly. And they actually have a word for the next thing. 10 to the 33rd bytes is a thing called the epic byte. Truly. So everything is data. So whatever you're doing on any kind of social media, you're contributing to billions and billions, as a famous guy called Carl Sagan would say, billions and billions of things happening in every minute on the internet. Data everywhere. And so the fact that we're creating this data, we also ought to be creating value from data. So like the internet is a lot like ancient Egypt. People used to write on walls and worship cats. Well, anyway. So the most important thing is value creation from all this data. So value creation means products. So if you think about recommender engines, how many people have ever used a recommend engine? You know what one is? If you go to the website and it says, hey, people who bought this book also bought that. People who viewed this movie also viewed that. So every e-commerce store has stuff like that. They recommend things to you, right? We've all seen this, right? So there's a company out there whose entire business started as basically selling stuff and recommending more stuff to people, called Amazon. Amazon is $1 trillion business. One of the couple $1 trillion businesses in the world. There might be three: Apple, Google, Amazon. 30% of the revenue, 30% of the revenue of $1 trillion company comes from a machine learning algorithm, the recommender engine. So there's one little bit of mathematics you learn about finding patterns in data such that you can predict the future, just like that NBA play-by-play history. That little bit of magic you can do by looking at those historical data and seeing what might be the next best thing, whether the basketball court or a product you might want to buy when you're shopping online. That little single algorithm is worth 30% of the revenue of $1 trillion company. I don't know about you, but I think anyone would want to be part of that story. Digital everywhere, digital everything. The world is digital. The problem that tends to happen with businesses, and we're getting past this stage now, but historically, they have these things called data silos, right? You have sales data in the sales department. You have customer call center data in another department. You have returns of defective product information in another department. You have marketing data about what things we should produce and sell in another department. You have all these different silos that don't communicate. They don't connect. And it's like the blind men and the elephant story. Anyone ever heard of this sort of little story? So the idea was that these blind or blindfolded men are feeling a different part of the elephant, and they don't really know what they have there, because they only feel a certain part of it. So one of them is feeling the ear, and they think it's a fan. One feels the tusk, and they think it's a spear. Right? Another feels the leg, and they think it's a trunk. Another feels the tail, and they think it's a rope. So they all have a completely different description of this thing because they're only looking at that limited view of the larger complex system. So until they get their blinders off, they really don't understand the full complexity and power and capability of this complex system. And so as companies and businesses, government agencies, everybody's sort of taking those blinders off. In other words, they start blending the data from different parts of the business. They start getting these deeper insights into the customer, if it's a customer, if it's a sales company, a marketing company, or a product company. Or maybe it's a medical company, a hospital, clinical analytics team, or something like this. The unknowns about the patient. We're not connecting all the bits of information about our patient, but once we connect all those different insights, we can do better to deliver better health care. So all these ways of getting that full view of the thing helps to understand it better and to build better models to understand it and to produce better products to serve that thing, whether it's a human or a machine or whatever it happens. So some people got the mistaken notion that in the era of big data, which is sort of what we've been talking about the last 10 years or so in this field, they think, oh, I have lots of data. But if you just add more data, you're not necessarily solving any problems, because you still have to fight the cultural battle of people sharing their data with one another. All right, so if you ever work on projects as teams, hopefully you will. If you ever have data hackathons, which I presume you may, it's all about sharing data, sharing insights. Different people in the different teams will share insights and see different things. So it's really the combinations of all the data that's really most important. It's the ways you combine things and put them together that you start seeing the interesting insight, because I never looked at it from that perspective and this angle, like the blind man taking the blindfolds off. Okay, so if you think about the growth of data, people always like to say, wow, we're living in this exponential age where data is growing exponentially. Okay, so you all know these formulas, right? So linear growth means something like 2 times x. Exponential growth is like 2 to the x. Well, if you look at all the combinations of everything, like if you have like 10 things, 1 with 2 and 1 with 3, A with B, A with C, A with D, A with B, A and B with C, A and C with D. I mean, all those combinations, it grows like x factorial. So there's x factorial combinations of x things, which is roughly x to the x power. That's a bit faster than 2 to the x. When x gets to be a big number, that's way faster. Okay, so combinatorial growth is crazy compared to exponential growth. So the next time someone says to you, and I actually say this to business leaders all the time, next time someone says to you that, hey, we have an exponential growth of data in our business, just say to them, so little? Because really the power, the insights come by the combinations. Not by how much you have, but by the number of ways you combine it to look at all the different perspectives. I had a student who worked with a Galaxy database. It was a single spreadsheet, 26 columns, 3,000 rows. It was less than a megabyte. Nobody in the right mind in the big data world would say that's big data. An Excel spreadsheet, less than 1 megabyte? I mean, it's not even approaching a gigabyte. It's not even, I mean, it's a billion times smaller than a petabyte. Where are you, man? That's not data. That's not big data. Well, my student, I had him start analyzing all the different combinations of those 26 properties of galaxies. The sizes, the shapes, the brightnesses, the distances, the star formation rate, all kinds of things, 26 different properties. Look at all the principal component analysis and clustering analysis and regression analysis. Do all the different statistical tests you can imagine for all the different combinations. So it took him a day to do all pairs of things, A with B and A with C and B with C and A with D. And it took him a day to do that. Then it took him 2 weeks to do all triples, AB with C and AB with D and AC with E. I mean, all those combinations. It took him 2 weeks to do all triples. It took him the rest of the semester to do all groups of 4, ABC with D, ABC with E, and so forth. I asked him if he wanted to continue during this summer project with me to continue working on this, and he said no, he had other things to do. And I said that's a good idea. Because based upon the rate at which you were moving, if you were to do all 26 factorial combinations, remember this is just a little spreadsheet, you can look at it on the screen, 26 columns. It doesn't matter if it had 3,000 rows, it could have been 100 rows, it could have been 50 rows. So the number of rows is irrelevant, it's the number of columns, number of combinations of those columns. I said if you wanted to do all of those, it would take you 10 to the 9, that is 1 billion, it would take you 1 billion lifetimes of the universe to finish this project. Say it again, it will take you 1 billion lifetimes of the universe to analyze a trivial little Excel spreadsheet when you look at all the combinations of variables. So it's not the volume that's the big value maker, it's the variety that's the big value maker, the big discovery. Again, take the blindfolds off the blind men and start finding them. So the title of the talk is the top 5 things to know about data science. The first one was the data. The second one is the science. In fact, if I had ever had to stop the talk right here after this slide, that would be fine with me. Because I always tell people the 2 most important things in data science are the data and the science. That's probably hard to remember. 2 most important things in data science are the data and the science. All right, not a joke, it's a fact. Because it's the data that is our fuel for discovery. That's the insight, that's the raw objective evidence that we need in order to understand our world, understand that patient, understand that customer, understand that jet engine, understand whatever. The data is the raw objective evidence that we're collecting to understand that. How did that person use that app? What product did that person buy? What products did this person like? All that kind of stuff. And the science is the process, the methodology by which we do discovery. We look at the data, we see some pattern, we infer some hypothesis to explain it, we design an experiment to test that hypothesis, we run that experiment, analyze the data, and then we either validate or refute our hypothesis, then we refine it and improve it. All the while trying to reduce error, improve accuracy. It's a process, it's a procedure. It's not science unless you're following a scientific methodology. Sorry. Okay? So some people will say data science is R programming, or data science is Python programming. Granted, you need those things, but that's not what science is. It's a tool of science. It's not science. Writing code is not science. It helps science. It's great for science. You need it for science, but it's not itself science. All right. Creating new codes, yeah, that's science. Because it's creating something and testing to see whether it works and refining and improving. That's a scientific process. So for example, a lot of times we talk about, when we measure accuracy of something, we go to a diagram that looks something, not this diagram, but we use what's called a confusion matrix. How many things did you get right? How many things did you get wrong? So for example, let's say we go to, what's a good example? Okay, detecting potential terrorists in the airport security line. All right? So if you let if the TSA, Transportation Security Administration, lets someone through the line and board the plane, they're saying that that person is not a terrorist. Okay? So that I don't confuse my terminology here, we're trying to identify safe passengers. So this is a safe passenger. That's a positive person. Positive. So if that person truly is a safe passenger and doesn't do anything bad, that's a true positive. All right? If you say someone is not safe and you pull them out of the line, you frisk them, you take out their bags and go through all their luggage and they miss their flight and then they get upset, and it turns out they're a perfectly safe person, but you thought they weren't, that is to say, you're saying they're not a good safe passenger, that's a negative prediction. But it's a false negative because the person was actually okay. Okay, so true positives are good, false negatives aren't so good. What about the other side of the coin? What if you actually have a terrorist come through the plane? What if you have a real person planning to blow up the plane? All right? And they get stopped at the gate and aren't allowed to board and they get taken away. All right, so they're identified as a negative and they're stopped and they aren't allowed to board the plane. That's a true negative. That's also a good thing, a true negative. What about the one that's left, the false positive? Who's the false positive?
Terrorists allowed to pass.
The terrorist who you say is a safe passenger and they're allowed to pass. All right, that's a false positive. You're saying they're okay, but they're not. All right. So what you want to do when you build any model, whether it's cancer classification or terrorist classification, or that little recommender engine that Amazon makes 30% of the revenue off of, you want that thing to be as accurate as possible. You don't want to waste your resources on something that's wrong. You want to get that prediction as accurate as possible, just like those play-by-play histories for those NBA teams. So you want to minimize the number of things you got wrong, the false positives and the false negatives. So normally accuracy is measured by how many things you got right, the true positives plus true negatives divided by the sum of everything. So I have an idea. I go to the TSA and I said, I got a system where you don't need all those cameras and x-ray machines and those long lines at the airport. My system will detect, in terms of accuracy, overall accuracy of true positives and true negatives, overall accuracy of 99.999999999%. Just get rid of all that stuff. My model is 99.9999999% accurate. Wow, fantastic, Mr. Data Scientist. How can we use your model? My model says let everybody go through. Because only 1 in a billion is going to blow up the plane and kill people. What? No. Well, what you just encountered there was part of the scientific process. That is a useless, a poor model. Because the cost of a false positive, that is letting that terrorist pass, is way more than the cost of a false negative. That is some grandma who misses her plane because you're going through her icy beams. Yeah, there's some cost. You probably have to pay these people compensation for missing their plane. There's some cost associated with people missing their plane, and they might get irate and might tweet something nasty. But nobody died. So the cost of a false negative is immensely different than the cost of a false positive. And when you build a model, you have to recognize that. So don't just declare that my model is 99.99% accurate. Sometimes the model that's 80% accurate is way better. Because that 80% model might have no false positives, that is, you never let a terrorist through, and 20% of the passengers get detained and have to go through those crazy lines. I'm not saying that's we want 20% of everybody detained, but I'm just saying sometimes the better model is the one that has less overall. So the scientific process is to understand that you don't build one model and stop. You talk to the people who are going to use it, you have domain knowledge, You get that feedback and you feed that back, that information back into the model. So when people talk about the scientific method, I hate that when they say that. I actually just said it myself. It's really a cycle. It's all about collection, formulation, hypothesis, experimental design, evaluation, review and refine. It's all this, it's a cycle. It goes around and around until you're satisfied that it's accurate enough. And all the way through this, there's always a lessons learned, that is things that fail that you want to get better the next time you iterate on the model. All right, so there's all kinds of literature about the importance of embracing failure. Thomas Edison said it himself. He said, people complain that he failed 1,000 times to build a light bulb, to invent the light bulb, and he said, no, I learned 1,000 ways not to invent a light bulb. In machine learning, people do much machine learning yet? You learned some mathematics of machine learning yet? All right. So one thing you do when you measure accuracy of a model, again, if it's 99% or 80%, I don't know if that's good enough. So I refine my model and I measure it again. So after I did the refinement, after I did some changes, did it get better or did it get worse? It's important to know that, right? Because if it got better, I want to keep going in that direction. If it got worse, I want to turn around and go the other direction. I want my accuracy to improve, right? So what you learned in probably 5th or 6th grade is this little thing called the equation of a slope of a line, right? How do you get the slope of a line? Can you get the slope of a line from one data point? No, you need two, right? You need 2 points to get a slope. So how do you know if your model is good enough until you fail twice? So I always tell people, especially when I do interviews, I said, tell me about times you have failed. You're not a good data scientist unless you've failed at least twice on each project. If you can't explain to me how you failed at least twice on a given project, then I question whether you're a good data scientist. You might be a good Python programmer, but you're not thinking scientific. That is, if it's 80% accurate, how do you know that's good enough? And then if you change it and it goes to 85, do you stop there? Hey, if I'm doing good, do I just stop? No, I want to see where the peak is, and then you find the place where the slope change goes to 0, right? So if you've had any calculus, you know what I'm talking about. You find the extremum of the function, the maximum of the accuracy curve, or the minimum of the error curve. And you only find that by what they call sliding down the hill or climbing the hill. Okay, using that slope to find that extremum, that optimum point. So it requires at least 2 points to get a slope. So you have to fail at least twice as a data scientist. So embrace that. It's cool. I'm cool with that. So please talk to you about your failures when you come talk to me. That's okay with me. I have no problem talking about failures. Okay. So the process is scientific. Whether it's machine learning or science, it's about the process of learning from errors. In machine learning, we call that back propagation. That is, given the error, how much, if the slope change was this much versus this much, you might want to sort of creep along if it's this much, because you might all of a sudden be sliding down. If you're going rapidly uphill, then hey, you can take a big step because I project it's still going to be pretty good. Anyway, so back propagation is a very mathematical process I want to talk about, but it's all built into the machine learning algorithm. And so I like to say that, in very colloquial language, that training machine learning algorithms, training these algorithms by learning from these errors, is a lot like raising teenagers. I've raised a couple. Raising teenagers. There's an expression that applies to both machine learning and to raising teenagers. Good judgment comes from experience, and experience comes from bad judgment. That is to say, you make a mistake and you learn from it. Then you do better the next time. So good judgment comes from experience, and the experience comes from bad judgment. That's literally a colloquial way of explaining the deep mathematics of back propagation and neural networks. If you ever read a chapter on that, they won't have that sentence. But I hope you remember it. All right. So here's an example. Okay, so let's say we're testing someone for the coronavirus. Oh wow, that's in the news a lot lately. Okay, so we have some kind of medical test. Okay, so the drug companies are working feverishly to do a detection, detecting whether people have the disease or not, the virus or not. Okay, so there's this new test. This is all made up data, by the way. So if people who were not infected this is just a histogram of the number of people who aren't infected, with the black curve and the red curve of those who are infected. And what do these numbers represent is, again, it's made up data, so it's some test result, some lab test result, maybe your white blood count or something. It's just some lab test result after this with this drug, and you're saying this is the distribution of that lab test result for people who have the disease, these don't. So there's some overlap here. All right, so in this zone here, there's some false positives and false negatives happening. That is, some of these people, if they come back with a score of 1.2, you don't really know, do they have the disease or don't they? Do I send them home or do I quarantine them? You don't know. False positive, false negative. What's the safe thing to do? Send them out back to the street? Send them back to school? No, probably quarantine. Right? There's some costs associated with quarantine, but there's a bigger cost if people go and infect the whole classroom. Oops. All right, so so you can start to figure out, well, where do I draw that line? Here comes the scientific question. Or what's the cost? What's the associated cost between false positive, false negative? Where do I draw that line? Oh my gosh, I don't know. Someone comes up with another idea. Well, if we're trying to minimize the number of false positives, false negatives in this confusion matrix, we want as many things as possible on the diagonal, true positives, and true negatives. That's how we measure our performance. Realizing, again, there's a cost associated with these the cost is different. Someone comes up with the idea, let's do another test. Because these drug companies are working feverishly to do this. Again, this is a made-up story. These aren't true story. It's a made-up story. So another company comes along, hey, we got another test to test whether people have the virus, and here's our lab results. Is that better? Does it look better? Because anybody in this range, anybody in that range could have it or not have it. I mean, the infected population is completely consumed within the non-infected population. So you think to yourself, this hasn't helped. But what did you just learn about data science? It's the high variety of the data. It's all the different perspectives when combined that give you the insight. Let's do that. It doesn't look any better than the first test, but let's combine them. Oh, wow. Same exact data points from the previous slide. Now plotted on a 2D scatter plot. Same exact point. I didn't fudge it. There's now a clear separation between those infected and those not, because we're now looking at the higher dimensional data, the extra dimensions that we've collected from multiple tests, like throwing things at students, not a good idea. Let's make sure I go backward and forward. All right, we got that done. And if we look at the diffusion matrix up here, okay, the number of true positives versus false. Okay, a false positive is someone you said is a positive, but they actually don't have the disease. 5 of those. So there's 5 people you quarantined yet you didn't need to. There's one person you say doesn't have it, but they actually do have it. Okay, that's the one you need to worry about. Okay, I'm not here to do clinical science, so we're not going to worry about that one today. But we basically got 1 out of 2,200. So our accuracy is now, instead of all that overlap that we saw earlier, it's like 99.98% or something. So we're in really good shape compared to where we were. Again, looking at the higher dimensional data gave us that insight. Not test 1, certainly not test 2 alone, but the 2 together. So now, number 3, top 5 things you need in data science. Data science. Number 3, the data storytelling. So data storytelling is what I've been doing for the last half hour. I've been telling you stories, right? I told you about the basketball kids. I told you about the TSA. I told you about the coronavirus. So telling a story that connects with people is an extremely important skill. So people don't want you to stand up there and say, hey, I did a deep learning algorithm with backpropagation using the ReLU activation function with 17 convolutional layers and a couple of recurrent neural network layers. And they'll look at you and say, what the hell did you just say? Oh, I just figured out how we could solve that one last person who was the false positive, false negative. Oh, is that what you just did? Okay. So data storytelling is like this. Like Maya Angelou said, one of my best quotes of all time. People will forget what you said, and they'll forget what you did, but they will never forget how you made them feel. So I started with that story where 22 years ago, when that lady gave that talk, and I said to myself, if this data science stuff has this much power to change people's lives, I got to do this the rest of my life. I will never forget that thought, I'll never forget that moment. I'll never forget how I feel. I don't remember exactly the numbers that she used. I don't remember exact details. I don't remember anything she wrote on the chalkboard that day. But I'll never forget how she made me feel. So that's the impact you want to have with data. With the stuff you do, the skills you have, yes, technical skills will get you in the door. You'll win the day, you'll win the argument, you'll win the customer, you'll be remembered if you can tell a good story. And I don't mean story by something made up, something that connects with the human side of it. Because after all, this is being human. I mean, right? Long before we had books, there were oral traditions in every culture. Right? Stories were handed down through all generations for hundreds, thousands of years. This is part of being human. Those stories that connect us, that give meaning to it. And so when you think about all the things you're doing with data science and data mining, you're finding patterns in data. And you can start talking about decision trees and neural networks, support vector machines, all kinds of cool mathematical algorithms. But really what you're doing is you're finding clusters, you're finding correlations, you're finding surprising things, and you're finding interesting links and associations. So use that kind of terminology when you talk with people. What are you trying to do here? You're trying to find interesting segments in your data, different patterns, different groups in your data. People who have the disease, those who don't have the disease, and maybe those who are sort of borderline. Okay, different medical tests. One is very clearly distinct from the other. If I use these two medical tests, I realize that people who are sort of in that boundary region between 2 and 3 might have a chance of a false positive, false negative, because I understand this about my data. Those clusters are very close, those are not. So are you trying to identify segments and clusters in your data? Or are you trying to find correlations, given X, find Y? Correlations in your data. Given P1, I can tell you what P3 is going to be for each of these data classes. That's called predictive power discovery. There you go. That's how the NBA thing worked out. Predictive power discovery. You saw a pattern. Given this will happen next. That's predictive power. If you just stopped today, right here and now, with predictive power, predictive analytics as a skill set, you could go get a job at any company anywhere in the world right now. But what's better is prescriptive analytics. I see that correlation changes slope for Data Cloud 2 right about here. I don't know why. Oh, I got this other parameter, P2, so that it changes slope when P2 has a particular value. Yeah, so I can tell you what P3 will be for a given P1. Not to get this is made up data. But I see that it changes slope. The correlation strength changes. Now, if P2 happens to be something I have control over, which in statistics is called a treatment variable or a condition. If it's something that you have control over, that you can change, you can adjust, it's a knob you can turn, all right? So the dosage on a medication, for example, a doctor has control over that. That's called a prescription. In analytics, it's called prescriptive analytics. So what prescriptive analytics says that not only do I see this slope, P1, P3 versus P1, it doesn't continue in a straight line out this way. It actually gets better, and it gets better at a certain point. And if that P2 is something I can adjust, and we're trying to improve revenue or improve customer satisfaction or improve the wellness and health of our patients, if we can adjust something to make their lives better, let's do it. The doctor said, oh, you look like you're getting better, just go home. You'll be better in about 6 months. Well, gee, doctor, can't you give me something so I feel better sooner than that? Oh, yeah. You want that? Well, of course you want that. Why did you have to ask for it? Okay, so if you can do prescriptive analytics, then you're really in a good set for a job. Okay, so class discovery, correlation discovery, which is both predictive and prescriptive, but the prescriptive only comes when you have those extra dimensions. Here we go back to the elephant story again. The extra dimensions to give you the extra insights that you need. Again, look through your data. Maybe some of those things that you don't have control over, they just happen naturally. If that's some things you can adjust, like the dosage on a medication or the sale price on a thing that's promoted on Amazon. You have control over certain things, and you can entice the better outcome that you want. You can produce a better outcome. I think the coolest part of sports, I don't know how many people are sports fans here. I think the coolest parts of sports, or games sometimes, you see a coach, and I've seen this several times, a coach will do a certain thing in a certain condition in the game, and now specifically football, I'm a big football fan. When it's a certain set of downs and yards to go, they do this one thing over and over again. And so the other team expects it to happen again. And then at the end of the game, out of the blue, the coach just does something completely different and throws the bomb for the winning touchdown. How did that happen? They never did that before. All right. Well, they set up a mindset that you're going to predict the next play based upon what you saw in the past, but they know that you're now in that mindset. So they do a prescriptive thing. They're going to do something different that's going to adjust the outcome to something way more optimal. Yeah, you can get 6 yards off that play, but I'd rather get 60 in the touchdown. 60 yards in the touchdown. All right, so prescriptive analytics is way more powerful. So you got these things, you get surprise discovery, sometimes called outlier detection. That's so negative. Outlier detection, anomaly detection. That's what they say in the statistics books. That sounds so negative. I like to call it surprise discovery. All of my PhD students, pretty much all of them, did something associated with surprise discovery, finding the interesting, surprising, unexpected thing in the data. And then last but not least, it requires a different cartoon, as a link discovery or association discovery, sometimes called network science or social network analysis. Finding the interesting associations. This applies not only to social networks, but marketing attribution, money laundering, human trafficking, because it's sometimes the intermediary who's connected not to whom, but who's connected to someone else through an intermediary. That explains money laundering and human trafficking and marketing attribution and all kinds of stuff. Okay, so network analysis, graph analysis is probably the most powerful thing on this slide today. Because after all, William Shakespeare said what? All the world's a graph. Right? No, he said all the world's a stage. But if he was alive today, he'd say all the world's a graph. So what's a graph? It's about entities and relationships. Entities and their relationships. That's what a graph model is, entities and their relationships. What's the Shakespearean play all about? Entities and their relationships. All right, so yeah, you get the picture. Okay, so when you're telling the data story, tell what you're doing, what kind of pattern detection you're doing on the previous slide, and then describe it in terms of the business question. Okay, what is sort of the deployment and development stage you're talking about? Are you describing what happened in the past? That's descriptive. Are you predicting what's coming? Or what's happening now in real-time data streaming, for example, over a network? So we've got descriptive analytics and diagnostic, then predicting analytics. So we have hindsight, oversight, foresight. Give it extra dimensions in the data. That's prescriptive analytics. I call that the insight that comes again from like the blind men taking their blinders off. Now they have insight how this crazy thing works and how I can optimize it. And to this other kind of deployment, which is cognitive analytics, which is you allow your data to talk to you. Instead of going in there and answering questions that are given, let me find the questions I should be asking. That's more powerful. A lot of times people will say, go answer these questions. Here's the data. How much sales did we have last quarter? What was the profits last quarter? Break it down by the different stores and the different regions of the country, the different product lines we have. That's descriptive. That's hindsight. If you can predict what's going to come next, that's powerful. That's predictive analytics. If you can make a better outcome because you see market trends and you can start adjusting to do better, that's prescriptive. That's also powerful. But when you look at that data, you might start saying, well, gee, why is this happening? Why is this trend here? Why did the slope of that correlation change? Why is this new segment appearing in my population? Where did these customers go? I mean, start asking questions. So up here, you're answering the questions given to you. Here, you're finding the questions that should be answered. And I call that cognitive analytics. I call it the right side, because it's the right thing you should do with your data, the right thing you should ask of your data. Okay, that's the scientist in you saying, why is that going on? That's the human in you. I got grandkids now. I've raised kids. They have kids now. All kids do the same thing. They test the world. Why is that? What's going on? Let me put this in my mouth and see what is okay. It's human to question and ask questions, test things. That's being very cognitive and very human. So bring that to the table when you're telling your data story about your data, about what you've done. And what I like to tell people is this last line right down here. Okay? So a lot of times in the big data hype world, I lived through that. Okay, so I started doing this stuff 20 years ago. No one knew what I was talking about 20 years ago when I talked about data mining and machine learning. Then 10 years ago, all of a sudden, everybody knows what I'm talking about, but everyone else is talking about it, and it's all a bunch of hype. There are people who are doing real work, but a lot of people who are just talking to talk. They're just saying the words in a sentence. Yeah, we're going to use quantum computing and blockchain and machine learning and AI to end world hunger and cure cancer and solve all the world's problems. Hey, yeah, great, wow, cool, fun. What are you doing? Oh, we're going to use quantum computing and blockchain. Oh my God. Okay, so don't talk the talk. Then there are people who can walk the talk. Okay, so walk the talk are those hardcore data scientists. I work with plenty of them. You folks here in training, you're going to be able to do it. You're going to be able to do the hard stuff. Okay, you can walk the talk. So not only talk about it, but you can do the hard stuff. Right? That's walking the talk. That's what you're being trained for in programs like this, walking the talk. But what data storytelling is, it's talking the walk. And what I mean by that is you can explain the hard stuff now to someone. You can explain it in the language of the slides I was just talking about, the different types of pattern discovery, different levels of analytics deployment and development. You can talk about it in human language that someone will understand the hard stuff without you using the buzzwords of the hard stuff. That gets you further along in life than just being able to talk technical stuff to people, being able to explain it to them in language. So that's what data story is, being able to talk the walk. And I'm not saying talk the talk. Don't just use the hype words in a sentence. Describe hard stuff in words and ways that people can understand. All right. So, depending on the time I have available, I can tell you a data story. We're getting close to the end, so I'm going to save this. And if anyone wants to stick around at the end, I will, from your choice, I will do one of these. I know some of you probably have to go soon, so I'm not going to do that now. So neural networks, graph mining, clustering, validation, and association. Choose wisely. Okay? I won't do that right now because I know the time will be short. But if you can't stick around, if you want, I got some other data stories I can tell you. All right, number 4. Okay, we got through data and the science and the storytelling is the data ethics. Now this could be a full lecture, but even worse than that, it could be a full semester. In fact, I taught a full course semester on data ethics at the university, so we don't have that much time in the next 2 minutes. So other than to say this is very important. I mean, there's a whole discussion about bias in algorithms, about bias in how we build them, and bias in the data selection, bias in how they're deployed. That is, who benefits, who gets the risk, who gets the benefit of this particular thing. And so Kathy O'Neill, she wrote this book called Weapons of Math Destruction. That's pretty cool. So there's a tremendous amount of discussion in this field today. And again, it's been hours talking about this. I just want to emphasize the importance of it. I love this quote from a famous science fiction writer. Remember H.G. Wells, he wrote War of the Worlds and Time Machine and things like that. So he said this over 100 years ago. Statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. Well, I think that day is definitely here, don't you? I mean, I think this is definitely here. This person said in the comments that if you torture data long enough, it'll confess to anything. Okay, that's where you need to put that scientist hat on and be a little skeptical that they got 99.99999% accuracy. Well, maybe it's not really all that useful to have that model. Okay. Okay, so there's a link to the course I used to teach. Haven't taught it in several years, but the material's still there. Anyway, it's beyond that. I love this quote. It's now beyond doubt that the cigarettes are the leading cause of statistics. Probably true. I actually had a student start to work. And the other first day, I launched his PhD idea. I said, why don't you do a PhD dissertation to verify this? Do semantic analysis, natural language processing, and all the research papers in statistics, specifically in the social sciences particularly, and figure out how many papers are associated with different societal problems, like smoking cessation or addictions, alcohol addictions. He probably won't be able to prove the sentence, but I thought it would be a really interesting exercise, and he brought it back to his thesis professor and said, yeah, go do it. Okay. So his statistics research around cigarette cessation is really that big. We'll find out. Anyway. So normally I wear a couple pairs of different colored socks here, which I didn't today. I couldn't find them in my drawer, but this is what it would look like. And at some point during my talk, I tell a joke, and I won't do that under out of time, which requires me to do a little thing with my pant leg, and then someone in the front will always say, hey, you got different colored socks on. And if they don't say it, I tease it out. So say it. As if I had.
Hey.
I picked on you twice already. But you're a good sport.
Yeah, hey, you have different colored socks.
He's got a Manchester United shirt on anyway. He's pretty cool. So if the person now, you said it's every color. A lot of times people say, hey, you have different socks on. And I would say, no, I don't. They're both the same size. Why do you think color is more important than size? We get into these arguments about specific features in our data. You think color is more important than size. I actually think comfort is more important than the color. Okay? So when we get our data, we can start looking at things, and we have a very biased opinion about what's important. For example, back in my days when I was a manager at NASA, the last 2 guys I hired all wore blue shirts. I said, hey, the next person I hire better wear a blue shirt, or I'm not going to hire him. Well, that's a very limited perspective on what makes a good hire. And you can imagine where you can go with this in terms of all kinds of inequalities in the workplace, where we look at one dimension of a person and don't see the rest. We do the same thing with our data. We get into these arguments, okay? So we got this thing, this is again toy data, and from this person's perspective, it looks like a circle. This blue, I call it the blue direction. This other person has another dimension they're looking at the data, X and Y, so to speak. One person has X, another person has Y, the same object, and they're looking at it from this other direction, the orange direction, and it looks like a rectangle or a square. So they get into these arguments. It's a circle. No, it's a square. It's a circle. No, it's a square. Well, guess what? They're both right. They're both true. But neither one of them is the truth. The truth lives in higher dimensions than what your bias is showing you. The features that we select in our model is a form of bias. It doesn't mean it's a bad thing, because statistical bias is a real technical term. It doesn't imply that you're an evil person if you have statistical bias. It means you didn't fully capture the full dimensionality and structure of your data with the features you've chosen. It's like fitting a curve with a straight line. Bad idea, right? You don't fit a parabola with a straight line. Right? So that's called statistical bias, otherwise known as underfitting. When you hire someone based upon the color of their shirt, that's underfitting, that's bias. Okay, so in statistics and in life, we use the same word, even though one of them is technical and one of them is more human focused. And so bias is a form of what we were stuck in our low dimension and not seeing the full dimension now. So data ethics is really, moving along, we're getting close to the end here. Data literacy, one of my biggest topics. Again, I live and breathe on Twitter just for this purpose, to promote data literacy. So does this count as big data? Well, not really. But anyway, so if you go back to that spreadsheet I talked about, it's a pretty small little spreadsheet. You can take a billion lifetimes to the universe, so maybe it does count as big data. I don't know. Anyway, so data literacy. Okay. So I was sort of woken up to the importance of data literacy even long before I became interested in data science. So back in my early days, when I first lived in Washington, D.C., decades ago, a famous politician who won't be me, but decades ago, I actually heard this on the radio, heard this for real on the radio. He said he was shocked, absolutely shocked that half the students in this country score below average understanding access. What's wrong with that? I'll pick up you. What's wrong?
Average means that half.
Yeah, well, duh. Yeah, but anyway, so I use this sentence to start my data ethics class when I taught at the university. Because yeah, if it's a symmetric distribution, then the median and the mean are the same, and this should be true. So for a standardized test, of course half of the students are going to be the whole average. All right. But if it's a skewed distribution, then this is no longer true, and that's another kind of story. Okay, but it was just amusing to me that people will say these kinds of things. Half the people in this country have below the average income. Okay. Anyway, but again, skewed distributions exist. I get that. That's a whole other discussion, which is why it's a semester course. Okay. But it just sort of gets your mind to think when people say things and they're not, I would say, statistically literate in this case, and not even data literate in some cases. So data literacy consists of two things. One, being able to use data correctly, and one, how to use it ethically. And if you get the slides later, you can read the cartoons. I'm getting low on time here, so I'm not going to read the cartoons to you now. I have an online talk that I gave about my career, the longer version of what you heard at the beginning of this talk today. And I talk a lot about the importance of that basketball story I told you at the beginning, and the importance of promoting data literacy, and how this is changing students' interest in STEM. Okay, you're already in it, you're already doing it, but there's a whole army of people in the world, especially young people coming through school who have no interest in science and math, and they should, because their world requires it, basically. If you're doing art, if you're doing sports, we already talked about sports analytics, even in art and music. All kinds of stuff is using analytics now. It's everywhere. It's everywhere. So people ought to realize that the thing they feel passionate about, they need math and science to do it. And just like those students in New York City, as soon as you realize there's a connection there, all of a sudden the little light bulb goes off and the passion starts burning, and those students who wouldn't otherwise have graduated high school went ahead and did it. That's the passion we want to lighten. Okay. So you already got the bug, but I would say data literacy is is being able to converse with data, work with data, recognize data when you see it. Actually do this in a public lecture. I'll step through it fast with you. I ask people, is this data, is this, and oftentimes most people will not identify all of those things as data, but all of them are data. And every single one of them is data, whether it's images or text or time series or facial recognition or apps in your phone, everything is data. It's all data. Okay, so data literacy is recognizing it's there, recognizing that there will be patterns there, which can be predictive and prescriptive and diagnostic and all those other things we talked about. Recognizing that's when you start becoming bringing that data literacy to creating value for an organization. So data literacy is recognizing that numbers contain meaning. Oops. Okay. This is a real sign, and I think they were just poking fun at people, but someone was very data literate when they put this sign up. Okay, because no, you're not supposed to add those three numbers. Okay, so it's very humorous, intended to be very humorous. But some people just don't get the fact that it's supposed to be humorous. So numbers, data literacy is a way of thinking about numbers and their meaning. Okay? So for example, here's a picture of my 3-year-old granddaughter on her third birthday, very excited. Okay, so the number 3, very excited. That meant something, just like Commander Data says. Those with the most birthdays tend to live the longest. The data proves it. Anyway, so again, you are beyond I do sort of public lectures. I've actually done this in inner city New York. I actually have gone there and just invited people off the street to come to my workshop, and they spend 4 hours listening to me talk, and none of them leave. And it's free, so it's not money. And I tell them story after story after story. So we get to this point, I said, what do you see here? I see a receipt. Oh, I see data. Look at all that data there. What you bought, how much you bought, the day you bought it. All right, the categories of things you bought. Oh, I mean, there's just tons of data there. Who checked you out? You know, how you purchased it. It's just filled with data. That little receipt is just filled with data. Well, this person, Susie Lou, real person, Susie Lou, real person, I'm not making this up, she said, I see opportunity here. As a data scientist, when you see data and you recognize data, you see opportunity. She sees opportunity. She said, wow, you know those little thermal receipts, those thermal printer paper that comes out of the cash registers? That doesn't use ink, it just uses heat to make an impression on the paper. So the paper's coming out anyway, and the little heat generator in the thermal device is already activated anyway. There's no extra cost, really, to put any more stuff on that piece of paper, because it's just heat inducing something to appear on the paper. And she says, hey, how about I do a topic map? That's a cool data science thing, a topic map, which shows the distribution of the different kinds of products this person bought. Lumped into product categories like eggs and dairy, and seasoning and bakery, meat and seafood, drinks, snacks, frozen produce. Whoa, that's cool. Imagine putting that on every receipt across the country. I think she has a revenue stream coming here. Because she just actually edited just a little bit the API, open source API. She edited the API that is used in those thermal printers in 100 million mom and pop and grocery store and product stores all across the United States. I hope she's monetizing this. That was really a cool idea. And then you really start talking, what do those percentages mean? Is it percentage of my price? Is it percentage of my number of products? Is it percentage of the weight I'm carrying home? All that data is in the company database, how much each of those products weighs. There's all kinds of stuff you can do with that simple receipt. Amazing stuff, amazing stuff. Create value with data. So data literacy, be able to read data, work with data, analyze it, and argue with data. Do that. You can do that. So there they are, the 5 most important things in data science. Data, science, storytelling, ethics, data literacy. Be data brilliant. Oh, oops, one more bonus. Number 6, you. You, the one who does this. Now again, doesn't mean you go have a career as a data scientist. But when you apply data literacy, these pattern detection, pattern matching, pattern discovery skills, and whatever you do, and I mean whatever you do, healthcare, sports, you know, manufacturing, anything you do, there's digital data around it. You can be that person that makes a difference, that creates value in that space. Because you don't need a data scientist to tell you the data is valuable. You need one to show you that. One of my good friends on Twitter here said this. I don't have to pay him credit for this because he always gets a giggle when I said, I used your picture in my talk again. So it's about showing the value. So really at the end of the day, and this is a different list, but what I really look for are not the skills, that anybody can learn a new skill. Once you learn programming, you sort of got the idea. It becomes somewhat easier, hopefully a lot easier, to learn another program. So people can learn skills, people can learn new things, but it's what's in you that makes the big difference. The difference are these aptitudes. And I started talking to people about the aptitudes of curiosity and creativity and communication and collaboration. I started talking about that with someone someday, and I realized they all started with the letter C, so I got carried away. And I came up with 7 the first time I did it. I said, oh, sailing the 7 seas. Anyone ever heard that metaphor? You know, sailing the 7 seas. It's like the explorers of old. They would sail the 7 seas, right? And I kept on going. I came up with 12. So anyway, so being curious and creative, courageous problem solver, cool under pressure, continuous lifelong learner, extremely important. Because the world is changing rapidly. Technical skills changing rapidly. So yeah, you can learn new skills, but remember, they're all changing rapidly. Okay? So back in the day, like my grandparents, a long time ago, when they went to school, what they learned in school, my grandfather was a banker. What he learned about banking in the 1920s saw him through his entire career. He never had to go back to school. He became a vice president of a major bank in Louisiana. He didn't have to go back to school and learn new stuff because that knowledge carried him through. But that's no longer true. The knowledge overturn is rapid. Every couple of 2 or 3 years, there's a tremendous overturn of new knowledge in the world. So continuous lifelong learning. And like I said, data storyteller, communicator, collaboration, critical thinking, computational. Okay, seriously, yes. So computational thinking is just like analytic thinking. It's a way of thinking about the world. Acting, the world is computable. That's a way of thinking. That you realize the world is computable. I can do something with what I see and I receive. It's computable. Oh, you're a good listener. That's being consultative. Listening to what the customer wants. You're connected. And I mean connected in 3 ways. You're connected with all that new knowledge. You're connected with your fellow colleagues, learning from one another, working together, getting insights, working together. But you're also connected with yourself. You understand what's important to you. All right? Just like those students way back when. They were passionate about basketball. Right? And they never saw that there was a possibility they could have something to do with science and math in their life. But they connected back to that passion and said, yeah, I can learn this hard stuff because it matters to what's important to me already. So connect with that passion in you. That's important. And then community focus. It's a feature of the data science community with all kinds of online competitions. I don't know if you commit hackathons. There's tons of opportunity to give back, all kinds of pro bono ways that data scientists are being asked to come help solve problems in cities and communities across the world. It's amazing stuff. But I'll close with this quote in my final slide. I love this guy. He said this about shipbuilding, and I think it applies to data science because data scientists explore vast and endless seas of data. So he said this about shipping, but like I said, I think it applies even to us. If you want to build a ship, you don't draw up people to gather wood and don't assign them tasks, but rather you teach them to yearn for the vast and endless. We have an opportunity to explore vast and endless seas of data in our world today. Discover new cures. Yeah, we may find cures for cancer. Find solutions to hard problems. Yeah, we may end world hunger. Climate change. Okay. We may be able to solve these problems with the tools and skills and aptitudes we have. So let's apply them. Learn this stuff because you're going to have a tool set that will carry you far in life and carry your impact far in life. So thank you. Let's do that together. Explore our world. I have time for anyone who wants to stay to hear a story or two. But thank you all very much for your listening this time.